delta function excitation, then you're going to get an impulse response, right? So this is your signaling system. And for linear system, it tells you that the superposition is going to work, right? So suppose you have some arbitrary signal as your input, you get some output. And this output basically is a superposition of all the delta functions synthesizing this signal. And the output is generated by superimposing all the delta functions of, before this time t. In other words, it's like this. The output from this linear system is a superposition of all the impulse response before this time t. You remember this? Right. You can have some excitation. Delta function excitation. You have some output. And if you put another excitation right here, then you have another output. And the output is the superposition of this two. Then you put another excitation right here, and you have another output. Then if you add up all the excitations, then the output is going to be superposition of this three. And this is what this is telling you. Okay, physically. Mathematically, you write down like this. And there's a requirement for such an equation, but this makes sense to you, right? If you have this excitation, you have this. Well, initially, you have this excitation, you have this. And then you have the second excitation, you have this. And there's a time shift. This is also has a time shift. And then you have this excitation, then you have this response, and this also has a time shift. And then if you put this three into the into the system, with a time shift, then the output is a summation of these three. Okay, agree? Makes sense, right? This makes sense to you. All right. When we say this makes sense, this means that we agree with causality, right? Causality tells you that if you have excitation, you have a response. Equal. Makes sense, right? And then we also believe there's a shift in variance. If I delay my excitation for a certain time, the output is still the same, but it's shifted by the time. And we call this shift invariant. And then when I say that, well, if I have three excitations, then the output is a superposition of this. It's a summation. Then we also agree it's linear system. So we talk about causality. We talk about shift invariant. We talk about linearity. So from this common sense, in fact, we are talking about the three things: causality, shift invariance, and linearity. So with this, in fact, we can continue to write this into a convolution. Okay, because this is a shift invariant, so we run into convolution. So basically it tells you that if I have a linear system like this with an impulse response, if I send two impulses into the system separated by time tau, then the output basically is the summation of these two. And these two are also shifted by time tau. Alright, so from this, I hope this now it's just a common sense to you. Okay, Mark? Okay. It's not difficult, right? And so we have a tool to calculate upstream output based on some impulse response of the linear system. All right. Michelle, can you take it?
One more time, sir.
And the question for this?
No.
It's common sense, right? Intuitively correct. Okay. But in fact, in this calculation, we are talking about these three properties: causality, shift invariant, and linearity. Right? So you synthesize the input pulse from data functions, and then you synthesize the output from the impulse response prior to the time t. Okay. Before time t, we put all those impulses into the system. Alright, so now suppose I have a harmonic function as an input. Now this guy is a unit harmonic function expressed by this. Can I do it? Right? I can do it. 假设我有一个这个输入是这个样子。If I have an input like this, it's a unit harmonic function because this is j omega t dependence is a harmonic function. The amplitude is 1 because it's a unit harmonic function. Alright, we put it into this configuration. What will happen? But and just in fact, when you just put it into this expression, you find that this is just a Fourier transform. Okay. You end up having this output. You can do this calculation very easily. Just put it into this convolution. You end up having this. Okay, with some prefactor here. But then the interesting thing is that the output is also a harmonic function of the same frequency. So you put in something, you get the same thing out, except that it is there's a prefactor associated with it. And this prefactor is the Fourier transform of this impulse response. Okay. So this HF, in fact, is a Fourier transform of this impulse response. You read this before? How? So this tells you that if I have a unit harmonic function as excitation as an input, you get the impulse, the frequency response. But the Fourier transform of this impulse response is called the frequency response of the system, or sometimes we call the state function of the system. Okay. You have this result. And this tells you the frequency response of the system. Okay. So this offers you a convenient way to get the transfer function. The frequency response of this linear system is sometimes called a transfer function. Okay. So this is acceptable to you, right? 也接受。好，这个 well, when you study signaling system, this is tremendously important. Right? This tells you the response of the system in the frequency domain. It tells you the bandwidth of the system. So if I want to know this, then the easiest is that when you have a system, for example, I just view us like this. This is some sort of instrument, and I don't quite understand it, but I want to know the transfer function. How do I know? I just connect this to a sinusoidal function from a function generator, and then I measure the output. When I measure the output, I can construct this. If I just vary the frequency of the sinusoidal function and then measure the output, I can get this. You understand what I'm saying? If you want to have a simple way, to get the transfer function of this linear system, you can do a very simple measurement. All right, just put a sinusoidal function into the system and then measure the output. Then you get this transfer function. And this concept is going to be used quite extensively when you deal with optical materials and also the propagation of the wave in space. The space in the scope of this class is a linear system. So now in your presentation, you're going to see, in fact, when you transmit a wave into a material, you are doing this calculation, in fact. Okay? And therefore, the response of the material gives you refractive index. The refractive index is buried into this system transfer function. Okay. And then when we talk about diffraction, far-field diffraction in space, and also when we talk about Fourier optics, we'll come back to this again. Okay. But now you catch the point, right? When you deal with a linear system, the system transfer function is very important. Then to deduce it, you just send a unit harmonic function into the system. And then the coefficient of it is a system transfer function. And then in your presentation, you'll be talking about susceptibility. The material susceptibility, in fact, is the system transfer function of the material. So what are we going to get to this point? All right, so I'll let you start this part. 所以伟君你是第一个，麻烦你继续了。
我是那个是序号，然后我再抽序号。
Okay. So who's the first person to give the presentation?
李小龙。
Oh, you'll be the first. All right, good. This effort is to get you involved in the learning process. So I'm hoping that after you finish this class, you fully understand everything.
Talk about group velocity first. So it says that when we have, let's say, an electric field of two or more electric field of different frequencies, of slightly different frequencies, So the resultant electric field, is composed of their individual frequencies, and so these frequencies that you see, it is the fastest component of those individual electric fields, which is called the phase velocity, and which is modulated by another frequency, it's sort of the resultant wave, which gives you the group velocity. So there are another properties attached with it. So it says that the phase velocity could be greater than the speed of light, c, but the group velocity is always less than c. So in the later part of the presentation, I also asked this question: how could this be greater than c? It says that okay, I'll discuss that part when we come to that question. And this is the formula for calculating the phase velocity. It's omega by beta, but to calculate the group velocity, it's d omega by d beta. And yeah, this is the same part that I've written here. We'll discuss this more in the question.
Is there any question for this part?
I think when we come to the question, you can ask me more about that group velocity part. Okay. Okay. So we derive the Poynting vector. So we first use the vector identity here, and this is the vector identity. You can understand. And so here, instead of A and B, we use electric field and magnetic field, and we get this from using this identity. And so del cross E can be replaced by negative partial derivative of magnetic field with time here from the Maxwell's equation here. It's yeah. And this is the curl of the magnetic field, which can be replaced by this the current density and this electric flux density, the rate of change of electric flux density here. The terms are defined here, and then we come to here from when you even simplify this formula, we come here, and this j term is this sigma a squared, and we then apply the Gauss divergence theorem to obtain this formula here. So say it converts it into closed surface integral and the volume integral for this term.
Like give some physical interpretations, not just formulas.
Okay. I forgot to actually add a picture here. I had that in my mind. It's in my book. So let's say there's a volume. Let's say a spherical sphere, and the EM wave is passing through that sphere. So the Poynting vector actually tells you about the flow of power from that volume. That's what. So how much power is getting out of that sphere? That is what this Poynting vector tries to tell you, how much power it carries. So if we can integrate the power flowing out of that sphere, that is what the Poynting vector tries to tell about how much power that EM wave is carrying and in what direction. Also speaks about the direction. So okay, here. So that is how it is defined. Electric field, the cross product of electric field and magnetic field. That's how the Poynting vector is defined, and it also gives you the direction of power flow of electromagnetic wave. So also the magnitude plus the direction of the power flow, which is the direction of the propagation of EM wave. That is also the direction of the flow of power. So here we have taken one electric and magnetic field to get to this expression. And this is the phasor form, and we use these electric and magnetic field to, and this formula we put it here and get this expression, and you do the cross product of these two. We again try to simplify that.
You go back to the last page.
Yes.
We do a multiplication.
Actually, it's cross product for.
Right, but how do you connect this expression to the next one on your next page? How did you get the average result, average power from this?
So to get the average power, we integrate this for one time period.
Okay.
Yeah, we integrate this average power. So first we calculate the power expression, and then we integrate it for one time period, and that's how we get the average power.
Can I do the integration over 2 periods?
Over 2 period. To calculate the average, we should integrate it over one time period. Oh, I think if we do the integration with over 2 time period, then we must divide it by we must divide the expression by 2t.
Okay. Eugene, do you agree?
Because
你说
usually
可
to
不
get
可以积分2个 period？
Yeah.
可以吧？因为我积分是一个周期，但我还是把时间处理掉了。
Or can I integrate over 10 periods?
Yes.
usually to calculate the power, we mostly do it over one time period. That's how we calculate the time period, the average.
Okay, but does it make any difference if I do integration over 10 periods or 100 periods?
No different. It's okay. No matter 1 period or 100 periods.
If we do whatever period, we divide it by that that period.
Okay, and the result will be the same.
It will be the same. Yes.
Why?
Because that's how average works.
But because if you go back to the last page, the reason is that this guy is a periodic function,
Right.
so you can do any period average to get the same result. Exactly, in fact, when you do the 10, 100 period integration, this guy still goes to 0 because it's a periodic function.
Do we then divide it by the same period? If we do it over, let's say 100 period, will we divide it by 100 t?
Well, yes, you have to divide it by 100t, but what matters is this one. You have a function at this function t plus t that is constant integral over t over nt. You have this average of the integration, right? If this is a periodic function, suppose, and this is a constant, right? You integrate over whatever period, then you do a average over whatever period. N can be a large number, can be 1. Okay. Agree? But no matter how you do the integration, this integration is always 0. Which is a sinusoidal function. Basically, these two cancel each other. So the dividend is relevant to this one. This will be, this part will be B times NT over NT. So you always get this out. NT is good money. Alright. So don't just talk about formula. I'll give some physical concept. So the calculation is to extract this cosine phi from the calculation.
So we continue with the previous expression, and so here we have integrated for one time period the previous expression, and we get this as teacher showed us here. This is what came out of that integration, and this could also be written as the real part of electric field times the conjugate of magnetic field divided by 2. So that becomes the average power density, formula for average power density. It is also called complex Poynting vector.
So this is a shortcut for you to get the average power. Okay. What you carry is your average income, your average NT. Every month you get some money, and then you can save. But if income, outcome sort of compensate each other, you don't quite care about that. So this is the net consumption of the power all the time. So, but when you write down like this, it's just a mathematical convenience for you to calculate this average Poynting vector or average intensity. You can just adopt this formula, and the calculation can be very simple.
We move to the dipole radiation. So as we know that charge in acceleration produces electromagnetic radiations, and dipole could be one of the simplest picture of that. I've shown the dipole here for different compounds. Like here it's for sodium chloride, and here is HCl, because we were talking about dipole in material, so that's why I used that. So yeah, they oscillate in a material when an EM wave passes through the electric field, forces it to do so, and which generates electromagnetic radiations because of those dipole oscillating, and the intensity of those radiation, the angular dependence is directly proportional. It's like this, sin square theta, and it is inversely proportional to the square law, inversely proportional to in terms of radial distance. And it's also another property that the radiation is not in the direction of the oscillation, because it has to be, it cannot be in the direction of the oscillation. And this is the 2D picture of the radiation, and here is the 3D picture. So if you just rotate this radiation in 360 degree, what you get is this donut-like shape, which shows the intensity of the radiation. This is the 2D picture, and this is the 3D picture. and the one in the dark color shows the more intensity of the radiation. And now we talk about the electromagnetic spectrum. So EM waves are classified based on their wavelengths. So this is the whole the electromagnetic spectrum ranging from radio waves to gamma rays, and it is classified based on the wavelength. So radio waves have the largest wavelength in this order, and then we have the shortest wavelength here, gamma rays. And yeah, okay. And another interesting thing is that the visible light, the light that we can see, it covers a very small fraction of the electromagnetic spectrum, just 400 to 7 nanometer. That's all that we can see. So find it to be very small range. The rest of it we cannot see. So it's an interesting thing.
All right, this is very good. Now you want to connect the radiation to the concept of photon. That is the next page, I think.
Maybe I talk about photon. Should I get any question?
Any question about this? Well, especially I want to emphasize a little bit on the last page, okay, for the dipole radiation pattern. So let me give you one antenna like this. Okay, this is one antenna, and then you mentioned that you have charge oscillating. You have current oscillating on this rod, and sometimes that you accumulate a lot of positive charge here and negative charge here, and then next moment the charge will come down, the negative charge will go up. So you're going to have the current oscillating like this. And the strongest radiation is along the transverse direction. Why?
Because the radial dependence is like this, and it attains the maximum value.
Now I'm hoping that we don't rely on formulas.
Okay.
Do we have a physical picture? Why? Yes?
Because the dipole's oscillation direction represents the direction of electric field intensity.
Yes, very nice.
And since we have our radiation direction cannot be parallel to the electric field intensity. So that's the reasons why radiation's intensity will be less or close to nothing. The direction getting close to the direction of electric field.
Yes, it's governed by this, right? It's governed by this. You found that you have TEM wave, the radiation, the wavefront will propagate always perpendicular to the electric field direction. So if this represents the electric field direction, then Maxwell equation will require the wave to propagate strongly along this direction. So you get high intensity along this direction. But then you cannot have radiation along this direction.
So as we move towards this, the radiation intensity is lower, and finally in this there is.
Right. Yeah. Yes.
But if the oscillation direction is like this, why can't we have radiation close to it? Why? Why can we have direction that is not?
Okay, this
That is not.
is a wonderful question. But remember that this is not in the XY coordinate system. This is in the spherical coordinate system. Okay. So think about that. If we have this is a second question.
I didn't get the question.
But it's saying that if I have dipole like this, supposedly all the radiation will go along this direction, and you cannot have a radiation. You cannot have a radiation. Why do I still have radiation? Why do I still have radiation along this direction? I can have strong radiation here, and you can understand that, right? But why I can still have this radiation on this? This is the question, right? Am I right? Why? Why can I still have this radiation?
This part is, the formula is easier to explain here.
Well, this is a spherical coordinate system. Okay. Yes, indeed, you have strong radiation along the oscillation. Electric field is going to be along this direction. But if there's a certain condition that in space or in material or with some boundary, then in fact this component, this electric field can derive some components. You can do partial in space. You can always derive electric field along this direction that is perpendicular to this radiation direction. There's a partial components, and because it's partial components, so its intensity get reduced. Okay. So that is the reason. You have partial components. You can always derive the two perpendicular component, and one. This component is useless, so the intensity is reduced. But you can derive a partial component is big. That is why along this direction the intensity cannot compare with the intensity along this direction. But along this direction, the only component of electric field is along this direction, so you cannot have radiation. But along this direction, all the field components can go can produce radiation along this, so you get the strongest radiation. All right, so this is the explanation. Very good question. But sometimes you can have, if you put this cycle into some boundary conditions, and if the boundary condition only allow radiation along this direction, in fact, under certain condition you don't have this. Okay, but that is some specific condition that you are not allowed to do. You have oscillation along this direction, but you are not allowed to do this radiation. Then you can only observe this radiation. Okay, for example, the Snell's law require you to go through some boundary and then only go along certain direction. Then you don't have this radiation. Because Snell's law govern the input and output radiation. Okay. So that is another thing. But we're going to touch that part later. Okay. Very good question. Could you, we talk about the evaluation form. So next time you have to bring over some evaluation form so that we can provide the grading to the students. You remember that in the syllabus we have an evaluation form, so that you can grade the performance of the speaker. You have to bring it out and bring it to the class. But now this first time, so we just go easy with it. But I start to see the very good questions asked by you guys. All right.
So we come to photon. I think it's quite important in the later part of this class. So we have we know the dual nature of M wave. So it behaves as wave and sometimes as particle, and this when it interacts with the material, and this particle is what we call photon. And very good example of photo emission process, the photoelectric effect, where we see the particle nature of EM wave, the photon which ejects the electron out of the metal surface. So that's where we can see the particle nature. And yes, it also has momentum. It is massless. The photon does not have mass, but still has momentum. This is another question that I asked in the slide, and it's given by this. This is h cross, which is Planck's constant divided by 2 pi. This is I guess, propagation vector. That's how momentum is defined for photon. And there are some other terms such as photon flux density, and it is defined by this: the average number of photons propagating in space per unit time, per unit area. And this is the formula. This is the intensity photon. This is Planck's constant. This is the frequency. And another term associated with it is average radiation pressure, and this is given for absorptive, the surface that can absorb the photons. There are other type of surfaces which reflects, so the formula is slightly changed for average radiation pressure for such materials. But for the absorptive surfaces, this is how the average radiation pressure is defined. This is force per unit area intensity upon speed of light. That is all we have for photons. Any questions for this? Anything you found interesting?
Well, this is a little bit abstract because most of the time, especially when we talk about electromagnetic wave, we view lights as a wave. Okay, but then when electromagnetic radiation interacting with materials, then it behaves like a particle. So we need to make a connection between wave and particle so that we can understand how lights interact with the solid materials. Okay, turns out that there's correspondence, there's one-to-one correspondence between frequency and also wavelengths and momentum and energy. Okay, so this is sort of generated. The theory was generated in the early 20th centuries, and the connection is that the h bar k represent the momentum of the photon, and h nu represent the energy of the photon. Okay, but this is going to be well, even now it's not so easy to understand it. But when you talk about interaction between lights and materials, then this becomes very handy. Okay. So the conversion is basically the hk is the momentum, and then the h nu is the energy. Okay. But of course we can discuss even deeper. But for now, for this optics class, for now perhaps the concept can stop here. Okay. All right. Thank you. Very nice presentation, and I'm very much impressed by.
I'll try to include more physical pictures on the slides.
Yes, please. It's always good that yes.
I want to know. It is the P is the radiation pressure, right? And that is the average power. How can we? 那我怎么会相等？就是
Well, let me tell you the concept. Okay. When we talk about radiation pressure, we start to think about dropping things like this, and then the flow has a pressure. How do we calculate the pressure of the flow when I drop one particle? Okay, that comes from the force calculation. Right, this is momentum. It's not power. So when I calculate the when I try to calculate pressure, then I have to divide the whole thing with area. Am I right? Okay. Now, we need to extract the particle concept from photon. This guy is basically HP. Okay. And so when you calculate this, basically you'll be calculating this and then perhaps many momentums. But when I have particle drop to this, then the momentum is absorbed by this. Okay. But if it's an elastic scattering process with the bouncing of a ball, then I need to, for a single photon, in fact, the exchange of the momentum would be affected too. Okay. If I have a rubber ball, I drop it, it's going to bounce back. The momentum exchange is going to be 2 times. Okay, this flow is going to experience a force that is 2 times of the momentum change. One is positive direction, the other is the opposite direction, and then the time of the process is important. Okay, so this is how you calculate that. To calculate the radiation pressure. Okay, and if you calculate this, then of course this part is going to be the momentum of this particle. That is N delta V. Okay, but for the same formula here, you want to put in the momentum of the photon to get this pressure calculation. So if you go through this, you will end up having the expression on the last page. Okay. And then indeed, experimentally, you can measure this pressure. Experimentally, you can measure this pressure, yes. Okay. 这样可以吗？有没有回答你的问题？
那我的意思是它是一个，就是用电场跟磁场来看的话，它是一个 average power 吧，对吧？那我总觉得 average power 不是应该要？
不是 average power， 它是一个 pressure is pressure is not average power。
我是指
It's a force per unit. It's a force per unit area. It's not average power.
就是有电场跟磁场，就是时间计算出来，那是 force， 是不是？
No, it's a particle. It's a particle concept. Okay, it's a particle concept. And in classic electrodynamics, yes, you can relate the electric field, magnetic field to the pressure calculation. Yes, but the concept is it's just Newton's mechanics concept. Okay, if you throw a ball to some particle onto the surface, then this surface is going to experience some pressure. Okay, and then indeed you can calculate the relationship between the force and electromagnetic field. Yes. 那是在电动力学里头有类似的计算 yes. But here it's just a particle concept. You exchange of momentum and then you get pressure. 所以我不是很清楚 It's not clear to me your question or what your question is. It's not power. Okay.
Maybe because it is written as P, so
Yeah. Well, this P is not power.
I know.
It's pressure.
I know that's pressure. But 就是31页的最下面那边，他写的就是他看起来是 average power 啊。
对，它跟 average power 有关系。Well, it's related to average power, yes. When you do this configuration, because this is going to eventually give you the average power kind of conversion, yes.
就是我感觉应该要把 average power 可能除上时间，再除上那个 area 才会等于 pressure 吧。
Well, you can do all kind of conversions. For example, if I have a stream of particles with certain power, then you're going to see the similar thing, similar equation. Okay, for this case, n particle, and then there's a t, and then this will be a multiple of the area. But in this calculation, yes, you can convert this into power. Okay, especially this is more like h mu over c divided by delta t n particle 2 times divided by a. So this is converted to this, and this part is your power, yes. Okay, so you can do this conversion. And the same thing, so this is pressure, this is power. And the same thing if you have a lot of particles, which carry like n constant surface is absorbed, okay, so each particle is moving with the v, velocity v, and you have n particles, and then all the particles bounce back, so you have mv divided multiplied with 2 is the momentum change, right? And then it goes through some interaction time. Yes, then and also divided by area. This will be also the pressure. Let me do this. Force over area. I'm making an analogy. If this is just the particles, physical particles, then you do the pressure calculation based on this, right? And you can also convert this into power. Yeah, if I do, for example, square divided by v and the factor 2, and this will be my kinetic energy. This will be my kinetic energy divided by time, so that is power. So this will be more or less also power divided by some velocity divided by area. So you can connect power to pressure, yes. Okay. But at this moment, we don't have any calculation based on electric field and magnetic field. Okay. But of course, then later you can convert this into the Poynting vector, E squared to beta multiplied with some area, and this area cancel with this area. So you start to connect this pressure to the electric field. You can make such connections, yes. Okay. But this is not a point for calculation. Okay. This is a point that I can sort of think about electromagnetic radiation as a stream of particles moving in space, and then we can have a consistent results. Okay, so you end up having this intensity divided by the speed of light. Okay. Well, whenever you have a new theory, you need to be consistent with classic results, and that is sort of the consistent set of theory that allow you to view light as a stream of particles moving in space. Okay. All right. So could we have the next person to continue the presentation? Who will be the next? So each of them just did it. Who will be the next? Wait. Oh, Wei Jie, please. Well, I hope that this discussion can be very helpful. Okay. Through this discussion, I think you look deeper, better than that I stand on the stage and then just tell you a lot of things.
When the electromagnetic wave is lossy medium, its behavior is determined by the medium's permeability and conductivity. Such as conductor, the finite conductivity causes the wave to experience attenuation, and meaning that its amplitude decreases as it propagates due to the energy dissipation as heat, and the electromagnetic fields in such a medium satisfy the homogeneous vector Helmholtz equation, and K is the wave propagation number, accounting for the phase propagation and the attenuation. And the complex permittivity of a conducting material describes the propagation speed and the energy loss of the wave in conducting materials.
Okay, very good. Perhaps you can, well, next time, let's prepare the laser pointer for the student so we can point you where you talk. And there's a lot of information on this slide. Before you move away, you want to tell people a little bit more about the information on these slides?
你可以用滑鼠。
Yeah, 可以用滑鼠，上头有laser pointer。
就指过去啊。
可以指过去。Yeah. 啊？But there's a lot of information on this page. I know you read through this. You read through this part, right? But do you want to tell people what this is?
This is the permittivity in conducting material according to the formula. This equation.
Yes. What happens is that if you have, for example, some conductivity in the material, then you add the current term into the Maxwell equation, okay, into the Ampere's law. Then with this, you combine this electric field together, you come up with a complex permittivity. So this permittivity becomes a complex number. But when you consider propagation of the wave in the material, what do? You need to deduce the propagation constant of the wave so that you know that it is propagating in the material, right? But what is most crucial for talking about propagation is this propagation constant. But then you find something that is quite bizarre, because once you have a complex permittivity, your propagation constant will have real part and imaginary part. What does it mean? You have real part and imaginary part in the propagation. What happens is that your exponential J, K, Z, for example, suppose the wave propagates along Z direction. Now you have exponential minus J, beta, well, let's call it minus J, K, real part, Z, minus K, imaginary part. You have an attenuation term in the expression. Okay, so this is a consequence that you have a complex permittivity. So if you have a complex permittivity, this means that you have a wave that is the amplitude getting smaller and smaller. the amplitude getting smaller and smaller along z direction. Okay, so always give the people a physical picture when you talk about formula, and then bring out the key point so that it can be agreed by the common sense of your audience. Okay, so it's okay on this page. And this is a very important ability that in your career, you want to just propagate the key point and also idea clearly to the audience. So take this as a good opportunity for your education. Okay, so is this okay? Clear enough? All right, so if you have a complex permittivity, the consequence is that your propagation constant has a real part and imaginary part. And then this part means the wave is propagation, and this part means that the wave is going to attenuate during the propagation. Okay. All right.
This is about material dispersion. Dispersion. A material dispersion arises from the interaction between the electromagnetic wave and the bound charge in a material. And when an external electric field is applied, the dipole oscillates, producing a frequency dependent polarization in the material. And the definition of the dipole moment is the multiplication of the amount of charge and the separation between the charges.
Okay, very good. Anything else you want to tell people? Okay, but you talk about N, what is N? The capital N?
A number of dipole per unit value.
Okay, think about, for example, this material, this material, this material, this material. There's lots of electrons and also ion inside. And then one single unit is like this. But then, if you want to talk about the collective effect, then we have to add this into the model, right? Because we have many tremendous amount of dipoles in such a material. So then a single unit is like this, but then you multiply this with a single unit, then we'll be talking about the average ensemble effect of all the dipoles within a unit volume. And that is how we define polarization density vector. So this is dipole moment. If you multiply these two together, then that is the polarization density vector. Okay, 就是我们经常讲的这个 P. You talk about P, another P. Okay, eventually we're going to do this. Right? This is the electric field, and this is P. Or in fact, this is the frequency domain expression, and I'm sure that you're going to talk about this.
I'm going to talk about the damping factor. The effect of damping is caused by the energy loss during the oscillation, increases the frequency response, and as we can see, a complex N results in a complex here, and loss attenuation of the wave along the propagation direction. And the damping factor is responsible for the material absorption of an electromagnetic wave and between the height and the width of the resonance peak in the frequency domain. For excitation frequency below the resonance, the material exhibits normal dispersion, and where the
Can you point, use your cursor, a mouse cursor to point to where you talk about? where's the cursor?
Here. Yeah. 右下角。
Could you get the laser pointer? Well, do you have a PPT slides so that you can, when you create the, just a PDF? Just point to where you talk.
Oh, yeah, no more expression. And the refractive index will increase with the frequency, and the higher frequency complements travel more slowly than the lower frequency ones. Oh, yeah.
Okay. This is one dipole. Let's go back to the last page. Okay, you have a cartoon right here. So this is X. So imagine that this dipole is oscillating like this under some excitation. So a light instant on this is going to pull this dipole to do this oscillation. So the distance is going to change over time. We call this distance X. Okay, and when I do this, we hear something. In this process, there's some dissipation of energy. I start to have some heating, right? I start to have some heating here. So there's a damping because of dissipation of energy. So let's go to the formula. This one. So this is the displacement versus time, and this term describes, I start to feel the heating in my hand. So this is the heat dissipation, the loss of energy. Damping constant is due to this gamma, okay? And this related to the velocity I'm moving. Yeah? As I move really fast, I'm heating up my hand, okay? And this is just a resonant frequency of a spring. So this is sort of a spring model, and this driven force. Okay, understand this, right? All right. So I want to know the response of the dipole. This is only one single dipole. Only one single dipole. How do I know the response of this dipole? This is a linear system. All right. Let me put in one harmonic function at the very beginning of this class. I told you if I want to know the transfer function of the linear system, what do? Hey, I put in the unit harmonic function. Okay, this time, yes, I put a harmonic function. No. Where's the harmonic function? Right here, F. So the harmonic function is this. F is equal to Q, E, right? And this guy, I'm putting some unit amplitude function here on the T into the system. Do you still remember? Now this is the response, right? This is the response. Excitation is right here.
Yes.
So excitation is the electric field. The line is instant on this, providing this excitation. Let's put it, set it as a harmonic function. So when I put this into the system and calculate the response, this, look at this. This is the system's transfer function. That is why at the very beginning of this class, I told you that why we need to understand linear system. If you put a unit, this is non-unit harmonic function, okay, with some amplitude. If I put a unit harmonic function into the system, then I get the system transfer function. If I put this into the system, then I get system transfer function multiplied with this. So So if I get an answer of this is going to be equal to this amplitude multiplied with the system's transfer function. All right, I'm sure that initially you got it, right? This is the response of the linear system. And then you have a harmonic excitation. All right, so in the end, you get this. Look at that. This is your system transfer function. This is your excitation. So in this process, you get your system transfer function. Right here. 对吗？清楚 right? So if I pull out this for discussion, then I'm talking about the system transfer function of the dipole. But this is only one dipole. Let's multiply this with n. Then it becomes the total dipole moment per unit volume, because this n is the total number of dipole per unit volume. Turns out that this is the phasor of the polarization density vector. Okay, so this is the phasor of the polarization density vector. Polarization density vector is like this. So in fact, when we do this calculation, we talk about everything in the frequency domain. Okay, this is not a time domain results. This is a frequency domain results. Look at this. Right? Divide this to get the susceptibility. So you do this calculation, epsilon E. In fact, this is, now we need to specify. Those are complex numbers. And you get chi, the susceptibility of the system, and this is the complex number. And this is, remember that you have epsilon r equal to 1 plus phi d. Those are all complex numbers. And this is equal to n squared. So now you understand this, in fact, is the system transfer function of the dipole per unit volume. Right? So this is for single dipole. And then for many dipoles. And then you use this relationship to get chi, the chi E, that is epsilon r minus 1. The epsilon r is the square of the refracting index. So your refracting index becomes this expression. So when we talk about refracting index, it means it's a response, the dipole response of the material. And it fit with the electrical engineering training. In electrical engineering, you learn about the system transfer function, right? 频率响应之类的. So you also fit into this subject, right? So now is it clear to you? Okay, in optics we talk about refracting index. In fact, it's a system transfer function of the dipole system.
So I want to know what is the resonance frequency? How can I image resonance frequency? What is that?
Good. This is a good question. Can I erase this? Well, when you were in high school, this is wall, and this is a spring, and it's connected to some mass. You know there's the resonance frequency associated with it, right? My daughter has as a toy. That there is a spring, then you play with the toy, right? There's always a resonant frequency associated with it. So this system has a resonant frequency. You understand it, right? And if this K is the Hooke's constant, this resonant frequency is equal to, I remember this M over K Hooke, square of it, something like that. Okay. So a dipole, let's go back to the last page. A dipole of this, does it look like a spring? Yes, it looks like a spring. So there's a,
You oscillate like a bounded spring.
yeah. So there's a resonant frequency associated with it. But if you put this on a piece of table, there's a little bit of friction on it. Then there's a resonant frequency, yes, and then there's a damping factor associated with it. So is this clear to you? Okay, I can even do one experiment for you. A pendulum is also resonant frequency. It's also a resonant system. Okay. There's a certain resonant frequency associated with this, and this is associated with the length of it. The resonant frequency of this guy is quite slow. The resonant frequency of this guy is quite fast, and I can make it even faster. The resonant frequency of this is going to be larger. So this is also a resonant system. Okay, and what is driving it? My hand. My hand is driving it. Okay. And if the oscillation frequency of my hand, this is excitation. I just throw it away. If I'm driving this guy with the same resonant frequency of this, then you see the amplitude can increase. So let's go to that corresponds to a situation that the omega is equal to omega 0. This is an excitation frequency. Forget about this for a moment. If this is equal to this can be very big. Okay, do you have a drawing for the?
No, that's just
Okay.
which drawing, sorry?
Yeah, the imaginary part of it. There's a real part. And there's a imaginary part of chi.
It's there, but I think it's in your slide.
Because this part is responsible for the absorption of the energy by the dipole. Okay, so if my excitation frequency is right here, I can have a very high amplitude. Okay, if I match my excitation match to the resonant frequency of it, then you see that it's going to swing, continue to add up the energy. But what if my frequency is right here? We don't get response. Because the frequency is wrong.
The resonant frequency is the frequency at which it attains the highest amplitude. You
Yeah.
said that?
The frequency, this one matched to the natural resonant frequency of the system. Okay, for spring, there's a resonant frequency. Okay, and for this, there's a natural resonant frequency associated with it, given by for the spring. For spring, it's given by the mass and also by the Hooke's constant. Remember Hooke's constant, right? This is Hooke's constant. High school. Right. So for whatever resonant system, there's a resonant frequency associated with it. If you excite it at the resonant frequency, then the system can strongly absorb the energy. Okay, this is my excitation. So if I control my hand to this frequency and feed the energy into the system, you can take the energy very well. Okay? Therefore, you get high amplitude in the response. But then if I do this, the frequency is wrong, it just does not take it. It does not take it. All right. I have enough exercise to take. But I hope this is fun enough. Okay.
So in case of the spring system, if it is oscillating at its resonant frequency, it will attain the maximum displacement.
If you feed it with energy, right at this, it's going to move with large amplitude. Okay.
The maximum, we can say, right? For the resonant frequency, it will move the maximum. If it is oscillating at resonant frequency, then it would have the maximum displacement. Can you say that?
Well, I would say it's easy for the spring to take the energy to move with large amplitude.
Because in the graph it shows that at resonant frequency it attains the maximum peak, so that's what.
Yeah, maximum peak. This is a response. Okay, but there's no such a thing that about the maximum amplitude, no, because you continue to increase. Okay. And eventually this term is going to come out to kill the process. Okay. This cannot go up to infinite because of the gamma, the damping. Okay. But if you feed it with the resonant frequency, then the response can be big. Yes. So this tells you the response of the resonant system. All right. So this is clear. Let's continue to move down. Well, I like this discussion because after this discussion, I think you fully understand what happened. Okay. Yes. Well, you should be in charge. 就是说你要报告什么，你要讨论什么东西，你应该要有你的主见。
哦，我是说我是要继续报告，还是这是我们每个人提的那个问题？
对，就继续报告。对，然后把你的想法。把你的理解告诉大家，好不好？
How fast velocity can be greater than the speed of light? Because the fast velocity is just the speed of the wave phase, and not the speed of energy or information, and so it doesn't violate the reality.
Relativity.
Relativity.
Yes, in the theory of relativity, 这个是爱因斯坦的相对论。It tells you that the energy velocity cannot exceed the speed of light. Okay, and so it puzzles everybody that the phase velocity in fact can be larger than the speed of light. Okay, so eventually when you do the energy calculation, what comes into the calculation in detail is the blue velocity, not quite the phase velocity. Okay? And for this class, I don't think you will do the calculation. So this is a little bit simplified the answer that just tell the consequence, but not quite the rigorous calculation. The phase velocity indeed does not quite carry the information. But we can go back to your page. We talk about blue rusty and when we talk about blue rusty and face rusty, this envelope carry the 1010 information, right? So the information is the energy. So this is sort of reasonable that when you connect the blue rusty to the energy velocity, because the envelope of this carry information, but not the phase inside this envelope. Okay? And so the phase velocity can be larger than speed of light, because when you talk about information, you need to talk about blue velocity. Okay? So blue velocity is the energy velocity. But this is something even deeper. I prefer not to confuse you. Okay? But this is sort of taken by everybody. Right, anything else?
And the second question is what is the smallest and the largest possible existing wavelength of electromagnetic wave? And the smallest is the gamma rays on the order of 10^56公尺. And the largest is the radio waves.
And there's another additional question that I've asked. Can something be even lesser than gamma rays? Could it be even lesser? And EM wave of even lesser wavelength?
Well, certainly, yes. When you have, for example, earthquake, during the earthquake, there's electromagnetic energy released in the earthquake process. And you will also produce a very, very low frequency radiation. The frequency can be, for example, the 1 hertz or 0.1 hertz or 3 hertz. And that is how people try to predict the earthquake. Okay, if you go to Stanford, in the back of the Stanford University, there's a big low mountain, and they put a lot of antenna on the mountain, try to detect the electromagnetic radiation from the earthquake. Okay, the frequency is like 3 hertz, 5 hertz, this sort of frequency.
They also have a LIGO experiment set up, right? LIGO.
LIGO, that is for gravitational wave. That is not for electromagnetic wave. That's gravitational wave. But during the earthquake process, a lot of charges were generated on the Earth. And when you have charge generation, then you could produce electromagnetic radiation. Okay. So of course, you can have low frequency, even low frequency radiation. And this is and for the shortest wavelengths, this is more like limited by the ability of human being in terms of technology, the limitation of technology. Okay. So now, yes, you could produce like a 10 to the 16th meter wavelengths in the gamma ray range by colliding laser with the charged particles like electron beam, very high speed electron beam to produce this gamma ray radiation. Okay, very good. What else?
I'm sorry. I have a question of our previous question. I want to ask 上一个问题，想问这个问题，可以回到那个日本大师题。
The first page.
I know in the math, that is the phase velocity, and this is the group velocity.
That's the phase velocity.
Yes.
The first term is for group velocity.
Yes. This is因为我怎么想象这个速度，还有就是知道计算速度，然后omega 乘以贝塔，那如果好就是像贝塔，它是德就是去
Okay. This is a very good question. Let me try to answer you. Well, this is just a simplified picture for group velocity and phase velocity. Well, it basically tells you that for monochromatic wave, you only have single cycle radiation. Okay, it's a single frequency, so it's hard for you to visualize the pulse, the energy propagation. Okay, well, the way to visualize the energy propagation is to do this. Then it's easy for you to see it, right? The energy propagation is associated with this. So I do this. So I calculate the path, the time for this guy to reach this location, and then I can calculate the energy velocity.
And that is the group velocity, right?
And this is group velocity. Yeah. Okay. But when we talk about phase, we talk about wave. This is not a wave. But in any applications, we need to use a group of energy for doing the application. Okay. So the way to visualize this is to create such a pattern, group of energy, and to produce a group of energy for a wave, you need to add more frequencies into the system. You have to add more frequencies into the system to create group of waves to discuss the energy. Okay. The simplest is to have two waves to generate such a group of energies. But in fact, when we deal with laser pulse, it can be like this. And you will require some Fourier technique to produce this. Okay, you have to synthesize a lot of frequencies into this. And so you mentioned that when you talk about group velocity, that will be the velocity of this pulse, right? So you can agree that the pulse propagating from this location to this location, you'll be dealing with the calculation of this envelope to talk about energy velocity. Okay. So, but this calculation is not so transparent. You have to do Fourier transform. Okay. For example, the electric field. Do this 2 pi ft dt, you get this the frequency domain. So when you look at this, it's not so transparent in the calculation. Okay. So the textbook basically just pick up the simplest case to create such an envelope and tell you that the envelope velocity carries information, carries energy, and then tell you the concept of group velocity. Because when you deal with this, it's hard to understand it. Okay. So this is just the simplest illustration that hey, I need to add more frequencies into this system to create this, and then when I care about the envelope speed of the envelope, then the speed of this envelope is associated with this quantity. Because from this construction and from this photo, you can really calculate the speed of this envelope given by this equation. Okay. And then the phase velocity of this individual oscillation is associated with this omega over b. So this is a very much simplified model, just trying to illustrate the concept. Okay. But rigorously, you need to go through this Fourier analysis to eventually get this term. You have to add up a lot of frequencies, and that is also itself, the group velocity and phase velocity itself, are also the function frequency. Okay, but from this you can see that hey, the envelope carries the information. Okay, just like this, the envelope carries the information. Okay, I hope this to some extent you get your concept.
And I want to know, the group velocity is the omega over the beta. What is beta? Does the omega have the beta in the omega? 就是如果 omega 里面没有 beta， 那我要怎么做微分？就是它是一个什么样的概念？应该是 beta 里面可能会有，我也不知道。
Okay, let's go to the
关系。
Very good. Let's go to the dipole model. Okay, now you let's continue to go down. Now you have you just take the electric accessibility, right? It contains two parts, real parts, imaginary parts. And both of them are function of frequency, right? And then we have eventually we get K that is equal to omega over mu epsilon equal to K real parts minus J K imaginary parts, right? Because this epsilon is going to be equal to complex permittivity epsilon 0. This relative permittivity is going to be a complex number. So this is 1 cos pi epsilon b. And this is a complex number, right? So you're going to generate this 2. But this chi e is a function frequency. So this is the direct consequence of this. And there's a real part imaginary part. So your epsilon r is going to be your epsilon r is going to be equal to 1 plus chi e, right? This is a function frequency. So what does it mean? It means that your refractive index is going to be a function frequency. Okay. So this means what does it mean? It means that this k, if I write down exponential RJ k real plot v, this is going to be function frequency. Exponential RJ k r is a function frequency, right? And we call this that is function frequency. The propagation constant. Okay, so with this, you can plot frequency beta. Beta is a function frequency. So at a different frequency, right here, you have u omega over d beta. Well, this is equal to, conventionally we plot this. Omega beta. But beta is a function frequency. And then we do this slope calculation and get the group velocity right at this point. Right at this frequency. At this frequency. frequency to get the blue rust.
We studied the omega beta dispersion graph in the last class. Somewhere like
I'm sorry?
the omega beta dispersion graph. Is that what it is?
Yeah, omega beta diagram defines the dispersion, but then you can calculate blue velocity, phase velocity associated with it. And in electromagnetic wave, the dispersion could occur in the material. It could occur in the waveguide. So if you take the electromagnetic wave, previously we have the waveguide dispersion like this. This defines cutoff frequency. Okay. And in prisma, you also have this, and this guy is the prisma frequency. So you have omega beta diagram to determine the phase velocity. Phase velocity will be the slope of this line. This is going to give you the phase velocity. And then the slope of this is going to give you the blue velocity. So the important thing is that you plot this omega beta diagram for your system. Okay. And we just talk about this, so we can have an omega beta diagram to calculate the phase velocity, blue velocity at different location. But then for waveguide or prisma, you have different omega beta diagram, and we'll be talking about this in the electromagnetic wave class. Okay.
And the final question is, Volta's method is how come it can be as momentum? According to the relativity, momentum can also be expressed in terms of energy. Since photons have energy E equal to hf, so they also have momentum given by P equal to C over E.
Okay. Well, yeah, this is sort of the generalized concept for photons. Okay. And you see in the modern physics, again, the way I try to understand it is that this is sort of described in the interaction between light and materials. Okay. But when you describe light, interaction between light and materials, you need to have a whole new set of concepts to describe it. And then eventually people compromised and then sort of invented the concept of photon in this process. But you say that the photons is massless. How come there's a momentum? That is because we sort of first accept the Newton's mechanics first. Because in Newton's mechanics, you need to have a mass to have a momentum, right? And that is because in the educational process, we first learn Newton's process and then talk about momentum. But in fact, if that is not the ground truth, okay, the ground truth is something else, then you'll come to ask this question. Because in your mind, you already sort of prejudge that a momentum needs to have a mass. But turns out it's, Newton's mechanics is not the ground truth. Okay, there's even broader concept for the momentum. So you will ask this question because you think Newton's mechanics is a ground truth, but in fact it's not. So the question itself for this one is not valid by itself. Okay, when we was a small kid, we were educated with Newton's mechanics, right? And there's a definition for the momentum, and it needs a mass. But it turned out that the mechanics cannot describe a lot of things, especially in the fundamental level for particles and so on. So if you just extract the concept from Newton's mechanics and ask this question, well, then it's reasonable that it's understood that you ask this question. But if Newton's mechanics is not the ground truth itself, it's not true itself, then this question does not make sense at all, because it's based on Newton's mechanics. Okay, but Newton's mechanics just cannot explain all the quantum behavior of particles in materials and in the interaction between photon and materials. So I would just first reject this question, okay? Because Newton's mechanics cannot explain so many things in modern physics. Okay. All right. Anything else?
That's
That's it. But then you have additional set of the third set. So we should call the third person. Continue. Right. So thank you. 谢谢. Who is the third person? Okay, please. 你若需要 if you need to go to the restroom or need to walk, feel free to do that. Okay. But I think this discussion is very helpful. I'm hoping that you could be the person really leading the discussion. If you have very good questions. Okay. Yeah. Yes.
The first page, I'm going to introduce the Snell's law, about the Snell's law, and it related to the first restrict is that the wave we need to go through from N1 to N2, and N1 must bigger than N2, and in this condition it has law. It is the H law, and it must have the content is that it makes the electric field and the magnetic field must the continue in the boundary of the boundary law, and the electric field and magnetic field must continue in the boundary, and it makes the phase must the same because of the 7 and 8 equation, but I forgot to put the equation on it, but it has on the textbook, and it must make the equation, the phase same, and it also make the lambda same. So it comes to the Snell's law of the reflection, like the theta I must equal to the theta r, and the refraction is that Ni sin theta I must equal to Nt sin theta t. This is the first page of the content.
Okay. Did you make this page?
Yeah.
Well, next time could you just put some drawing to define theta I, theta r? Don't just write another textbook, another texts. Okay. Draw the diagram, and then you can properly explain the concept to people. You are not supposed to ask people to read the text on your slides. And nobody knows what equation 7 and 8, and you don't expect that people will just flip the text or hang out to find out what equation 7 and 8. Don't just describe formulas. Give the concept. Okay. Give the physical picture. Okay. Then let's go down to the next page. I want to see how it goes. Okay. No way. We cannot do this presentation. Next time, give the cartoon, the physical picture, define the angle, and so on. Okay. So I'm going to do it for you. Okay.
这是在3吗？
刚才不是讲完第一部分，是不是要衔接第二部分？
也要第二个部分，所以以前你这里好像跳掉了，是吧？
我们是好像是不可，
不知道，因为
第二部分只是
但它是用抽
对
顺序用抽。
对，所以你要跟着第二部分，然后继续下来，不能把你自己的这个 slide 拿出来，好不好？Okay, you see that in this process we went through a few up and downs. You can take a seat. And the good thing is that we collected a lot of good questions, and you guys are smart, very creative, and also really looking into the every details. Another thing is that you do feel that hey, you need to build up some ability to talk, okay? And take this as an opportunity to train yourself to be able to talk. And from time to time, I will come to rescue you. So let me continue the presentation. So we talk about the propagation, refractive index. And then now we are in a position to talk about electromagnetic wave going through some boundaries, right? 是吗？现在差不多应该是 approximately that we'll start this topic. Well, so if you have a normal instance, you may have a normal instance between two direct boundaries. Then you have some reflection, you have some transmission. Okay, and from the electromagnetic theory, it's very easy for you to derive these two formulas. Very similar to the transmission line you learned today, just today and in the past 2 weeks. Okay, we have impedance, but now we have refractive index. Okay, so this is the wave going through some direct boundary, and also have some refraction. But if you study optics, you need to remember that the most frequently used material is glass. 玻璃是最常用的一个光学元件。 the refracting index is 1.5. So if you put 1.5 into this calculation and set N1 to be air equal to 1, then you get refractance roughly equal to 4%. Okay, so this is a number you want to remember. Okay, because we use glass as a material, optic material, so. Right, so but be careful that when we talk about reflection coefficient and transmission coefficient from the electromagnetic point of view, there's a factor you need to consider when you do this summation. Okay, and this is based on energy conservation here. So one thing you need to remember from electromagnetic theory, this eta is wave impedance. That is equal to mu over epsilon. And this is equal to eta 0. That is square root vacuum permeability, vacuum permittivity, multiplied with 1 over square root of epsilon r. And this is equal to 1 over refracting index. Okay. So when you convert this from electromagnetic theory, then you need to convert this eta into 1 over n multiplied with vacuum impedance. Okay, and then finally you have a relationship between this reflection coefficient and transmission coefficient. So this is for no instance. But if you have a instance with an angle, always give people this diagram, not just writing a lot of formula, okay, and also text. People cannot catch the physical picture. Now imagine that you have again material boundaries, and then you have a instant angle theta I. Then the Snell's law of refraction require the instant angle equal to the refraction angle. Okay, and then the transmitting angle has to satisfy this is Snell's law. And you learned this long time ago, right? All right, so this is understood. All right, what is the interesting is that if you have a refracting index N1 larger than N2, the refracting index here is larger than the refracting index here, then you will have total internal refraction. If you continue to increase this instant angle, then this line will eventually go to this line. Then you have total internal refraction. Under such a situation, you're going to calculate the attenuation of the field below this line. Okay, if you have an angle, instant angle larger than this critical angle, what happens is that the electric field is going to attenuate, exponential decay along this direction. And this is how you get this the so-called exponential wave expression. So please go through this calculation. Okay, in the handout, and then you're going to find that what happens is that when energy propagates back into the original medium, then your electric field is going to have exponential decay under this. Okay, came out. But this calculation is something that you have to go through by yourself. All right. Now, again, we calculate the transmission coefficient, reflection coefficient, subject to the electric field propagation direction. Okay. And last time we talked about propagation, so the electric field direction is important when you do optical applications. And if you go through the electromagnetic theory, then you come up with this reflection coefficient and transmission coefficient for TM propagation. TM propagation is that you have electric field on the plane of instance. How do you define plane of instance? the plane of instance is defined by the surface normal vector and the wave propagation direction. Well, to define a plane, you need to have two lines, right? To define a plane, you need to have two lines. One line is the propagation direction of the wave. The other line is the surface normal of this interface. What is surface normal of this plane? This is the surface normal of this plane. So if you have a material interface, this and this material interface, there's a surface, right? So this surface normal of the plane, and then you have a wave propagating down from this direction or from this direction, it's okay. So you have two lines. 两条线. Two lines define a plane. We call this plane of instance. 北军可以吗 ？OK， 两条线定义一个面。这两条线是什么面？是什么线？波传播的线跟这个 interface 的 surface normal。OK， 可以吗 ？OK， so once you define the plane of instance, and then you have the electric field on this plane, then we call this the P wave or TM wave. So now you understand how you define P wave and TM wave, right? All right. So with this, you can calculate the reflection coefficient and transmission coefficient. Well, it turned out that this is quite interesting. If you plot the reflectance, that is the square of this reflection coefficient. Reflectance is defined to be the square of this reflection coefficient. Because this is related to the square of this is related to the refractive power versus input power. And then this is the incident angle. You end up having this blue curve. Okay, and forget about this green curve for now. That is a little bit deeper, but now let's focus on this blue curve. Well, initially, at normal instance for this glass, I use glass as the example. At this normal instance, this is 4%. And then at a certain point, you don't have reflection. You have zero reflection. This is very interesting. You put this Bruce angle. Okay. So at a particular angle, there's no reflection. And then if you increase the instant angle, then the reflection shoots up. And this is why I call it external reflection. The reflecting index here, N2 is larger than N1. So you can consider this is a piece of glass. This is the air. 从空气到玻璃，我们叫做 external reflection. From a low refracting index material to a high refracting index material, we call this external reflection. Okay, but if we have an internal reflection, it's different. This blue curve. Well, if this is glass, it's an air. If this is glass, it's an air. First, you have Bruce angle. Second, you have also internal reflection. And this is internal reflection. Is this too difficult for you?
So for the Brewster cycle, there is no transmission, right?
There's no reflection. We are plotting reflectance versus angle. The reflectance drops to zero. So imagine that you have a piece of glass. imagine that you have a piece of glass. In fact, this is a piece of acrylic plastic material. I have a laser going this direction. I have transmission. And I have a little bit of have transmission. But then if you look at table, you have reflection. No, I can do it. Okay. You see transmission. And then if you look at table, you have reflection.
Yes.
But if I polarize my laser alone inside the plane of instance, for this case, my plane of instance is this plane. Right, surface normal is along this direction. And then I propagate my laser along this direction, so my plane of instance is this direction. So what is interesting is that if I could polarize my laser in this plane of instance, at a certain angle, you don't see refraction. That is Bruce angle. Okay, that is Bruce angle. But normally, if you send the laser onto some material interface, you have reflection, you have transmission. Okay, but at a certain angle, the reflection disappears. If you polarize the laser alone in the plane of instance. Okay. And total internal reflection is, I did it in the class, right? Total internal reflection is like this. You see transmission, you see reflection, but then if I increase the angle of instance, at a certain point, that disappears. All the energy will just shoot down. Okay? So let me do it. See, you still see transmission, but then if I increase the instant angle, at a certain point, it disappears. All the energy just goes down onto the table. And then you don't see any transmission up there. And this is total internal reflection. And then you can see a very strong laser line along this direction, inside this glass, inside this. Previously, the reflection is not so strong. You don't quite see a line inside this. But when the total internal reflection happens, you see a line inside the glass because all the energy just goes down. So this is total internal reflection. Usually you have to come over to see it, otherwise you will never learn it. Okay.
Can you just say again the Bruce angle?
Bruce angle is like if I have say this flat surface, and then you see some transmission, and then you see some reflection, right? But for this configuration, the plane of instance is this one, right? The surface normal is this direction. The beam is along this direction. So these two lines form a plane like this, right? And then you need to specify this as TM or P wave. For TM and P wave, that is electric field has to be in the plane of instance. So you need to first polarize this laser to be in the plane of instance. So the plane of instance like this. So your laser polarization has to be in the plane of instance. But now I don't have a way to control the polarization direction. Okay, this is not properly the polarized. But imagine that if I have a way to polarize this laser in the plane of instance, then right at Bruce angle, the yellow dot will disappear. There's no reflection. So that is fine. Okay. See, this is the normal instance, and then I increase the instant angle. If I increase the instant angle to this value, 56.3 degree, then the green dot will disappear if I set the polarization correctly. So this is Bruce angle. And you can do this easily in the experiments, so ribbon. Okay, you can do this experiment easily in the lab. Okay, you got the concept, right? It look like we still need to come here on Friday. We sort of, I'm hoping that this Friday I can finish this. Okay. But today, at least we went through the steps, and then I'm sure that you take away something that you never forget. All right? So that is the most important. So if we do it on Friday, I will continue to be here and finish this part. And then next week, we can continue the next 25 pages. Okay, but you more or less understand how we're going to run this. And I'm hoping that you guys can be can play the key role for this class. All right, see you on Friday.
Yes, I can. I'm the one in the E-class. You can see it.
Yeah. All we get the notification. Can we get the notification? Notification.
What is notification?
Like an email that you uploaded it on e-class.
My notification is so bad.
I should make it.
Today or tomorrow. I can upload. I want to be soon as possible.
是的，是的。